we've got the chain rule up here on the board. The derivative of f of g of x, this function composition, is the product of the derivative of each piece. We get f prime times g prime, but each derivative is evaluated at whatever we were plugging into the function. So what we were plugging into g was x. We evaluate g prime at x. What we were plugging into f was g of x. We evaluate f prime at g of x. And what I want to do in this video is explore, just through an analogy, why it seems reasonable that those two derivatives get multiplied together. In the last video, we talked about why they should both be relevant, why we should care about both of them. In this video, we're going to talk about why they're connected by multiplication. So I have this lovely picture here. It kind of looks like a person with two different sized ears, but that's not what I was trying to draw. This represents three different gears. Gears would be connected with teeth. I didn't draw those. But the idea is that when I spin this first gear, that's going to cause the second gear to spin. But the second gear spinning is going to cause the third gear to spin. So we've essentially got a chain reaction going on. Now I'm just going to assign some variable names to things. I'm going to say x is the number of times the first gear spins. So I'll put an x here. That's not the name of the gear. That's measuring the number of times that that spins. U is going to be the number of times the second gear spins. And that, of course, is going to depend on x, because I'm going to spin this one. That's going to start the chain reaction going. Okay? And then y, we'll let that be the number of times the third gear spins. Okay. And that, of course, is going to be determined by u, which is in turn determined by x. Okay. All right. So let's just see if we can get some sense of the relationship between x and u, and between u and y, and then build out of that the relationship between x and y. Now, if I were to spin x once, is that going to cause u to spin once or less than once? Hopefully you figured out that it's going to spin less than once. That's because basically the amount of the border outside here that passes through this point would have to be the same on both gears. And if I spin this once, the amount of that outside gear that goes around is one circumference of this. But that's not going to be a full circumference of this because this is a bigger circle. So let's just estimate. Let's say that spinning x once, spinning the first gear once, so letting x be 1, causes the second gear to spin half a time. Okay? So I could write that as du by dx equals 1/2. The rate of change of u, the number of times the middle gear spins, with respect to x, the number of times the first gear spins, is 1/2. All right. Now, I know that when u is spinning, that's going to cause y to spin. Sorry, when the middle gear is spinning, that's going to cause the third gear to spin. U and y aren't representing the gears, they're the number of times the gears are spinning. Okay. So, if I spin this middle gear once, is that going to cause the third gear to spin once, more than once, or less than once? Well, because the third gear is a lot smaller, spinning the middle gear, which is significantly bigger, once, is going to cause this to spin multiple times. Let's just estimate, let's say spinning this spinning this middle gear once causes that third gear to spin 5 times. So dy by du, the rate of change with the number of times the third gear spins as a function of the number of times the middle gear spins, would be 5. Now, I want to try to figure out dy by dx. If I spin this gear once, how many times will the third gear spin? Well, if I spin the first gear once, it's going to cause the middle gear to spin half of a time. But every full turn of the middle gear causes the third gear to spin 5 times. So if I spin it halfway, I'm going to spin it, the third gear is going to spin half of 5 times around, or 5/2. Notice what we've just said here is that dy by dx is this product. And I'm actually going to just, since 1/2 times 5 is the same as 5 times 1/2, I'm going to switch the order of those. We're saying that's dy by du times du by dx. Okay. We multiplied things. Okay. Now, the fact that we multiplied them hopefully made sense because this is a scenario of gears spinning that you're familiar with. And that sort of suggests why we multiply things. I want to point out that when I write my derivatives in this way, using the differential notation, this almost looks like a proof, but it is not, and I want to point out why. Okay, so here, basically, we had y being like our f of x, okay? And u was like our inside part g, and x was the ultimate input. And here I've just written things using differential notation, okay? It looks like we're saying, hey, this fraction is just the product of these two fractions, and those du's will cancel. Wrong. Okay. With this differential notation, we have not yet talked about what dy, dx, and du mean on their own. We have only talked about them as one symbol together for a fraction or for a rate of change. Okay? We have not talked about their meaning separately. We will be doing that later in this chapter. It turns out that those differentials, dy, dx, and du, do have a meaning on their own. But their meaning, when we separate them from the notation that stands for the entire derivative, they're going to be variables. And the problem is variables are allowed to take on a value of 0. And if du were taking on a value of 0, 0/0 does not cancel. Okay? So because du on its own is allowed to take on a value of 0, but if I were thinking of this as a literal fraction, dy by du, du would not be able to be 0 because it can't be in the denominator of a fraction. I cannot just cancel and say that proves the chain rule. But the notation certainly suggests the chain rule. And if we had an extra condition that du wasn't 0, then this would be a way of proving the chain rule. It's just that we don't have that extra condition, so that the proof of the chain rule is a little bit more complicated if we allow for the fact that, hey, for some functions, this isn't going to change at all. With this example, if I'm spinning x, u's going to be spinning. But there are certainly some functions that stay constant over various intervals, and then they wouldn't be changing at all. And so I've got to take that into account. So this isn't a proof, but it's very, very suggestive notation.